Hi, everyone. Welcome. So you're tuned into the webinar, Scripting at the Speed of Compiled Code, Vectorization. My name's Megan Guidry, and I'm the training coordinator here at NeSI. Before we dive in, I just have a few quick housekeeping items to cover. So for today's webinar, we ask that you keep your audio on mute if you're not speaking. Have a question, you can type it into the shared Google Doc anytime. I will grab the link and post it in the chat now so that you guys can all pop in there and know where all the action's happening. So there you go. That link that I just posted in the Zoom chat, that goes to our Google Doc for questions. Alex will also be checking in periodically to see if you guys have any burning questions. And of course, there will be time at the end for general questions. And lastly, the webinar video and slides today will be available on the NeSI website in the next few days. So if you registered for the webinar, you'll get an email once that's posted. And since the webinar is being recorded, I see most of you guys don't have your video on. So if you don't want to appear accidentally in the recording, make sure that your video is turned off. So let's see.
Off of the TV.
Right. Our presenter today is Alex Pletzer from NeSI's computational science team. And just a little FYI, Alex will be doing the webinar demo today on NeSI, which may make some of the commands a bit different. So if you hear words like slurm or are confused at any point, you can post a question in that Q&A doc, and one of our support team members will answer you. We're more than happy to clarify anything that is discussed in the webinar there. And cool. Now, before I pass things on to Alex, I have a silly little example to demonstrate why it's important for us to know about vectorization. So, suppose your job is to move 100 jelly beans from a jar to an empty plate. And let's also say that you have two tools you can use that you can choose to get the job done. You can use tweezers or a ladle, which is just a fancy scoop. So which tool would you choose? Choosing tweezers for this task would be like using a for loop. They operate on each loop item individually, and a lot of time is wasted repeating the same action over and over again. So as a result, it takes quite a long time to move 100 jelly beans from the jar to the plate. Choosing the ladle for this job, on the other hand, is like vectorizing your code. Vectorized code allows operations on multiple items to happen in parallel, just like a ladle allows you to move many jelly beans all at once. And the result is code that runs much faster. So with that in mind, I'd like to pass things over to Alex, who will show us how we go about vectorizing our code. Welcome, Alex.
Hey, hi everybody. Thanks, Megan, for the introduction. I'm going to present vectorization because that's just one of the techniques that we have encountered as part of the consultancy effort or program that we offer to users on NeSI platforms. And during these consultancies, often we have to accelerate or make a given code run faster. It's just one of the techniques. Thanks, Megan, for that nice little example. We should also point out that in Megan's example, she had jelly beans of various colors, green, red, and orange, and yellow, and so forth. And it's vectorization always works much better if you just want to scoop all the jelly beans, irrespective of the color, the size, and these kinds of attributes. So although vectorization can also be used, for the more for the cases where you want jelly beans, only the green ones for some reason, in principle, it tends to work better if you're not too selective in your choice. But anyway, so I'm going to share my screen. Hopefully everybody can understand me. Yeah, everybody can understand
Alex,
me?
I don't know if it's just me, but you seem a little bit quiet. Is there any way you can make your audio like a bit louder? I don't know. It could be just me.
Is that better like that?
I can hear you. So yeah, I guess that's okay.
Okay, I'll try to talk louder. So anyway, I'm going to share my screen. We have some material here which I can share the URL. Let's see. Stop sharing. Not annotate. Sorry, that's not the one I wanted. I wanted to more. Okay, chat. So this is the URL. We're going to follow essentially the what we have here in these web pages. The code is called Python scatter, and it's a pure Python code. The vectorization we're going to talk about is going to be applicable to scripting languages. That means Python, MATLAB, R, to a lesser extent Julia, but to some extent it's going to apply essentially to all these languages as well, although the examples themselves will be using Python only. Okay, so you can actually run things as I'm speaking. So I'm going to type some commands, and people are welcome to type the commands at the same time, or they can just sit back and relax and just watch what's going on. There should be enough time to do both. You can actually run the example on your laptop if you have Anaconda, NumPy, and SciPy installed, or you can actually connect to the NeSI Mahuika, for instance. All right. So we're going into the. We have a couple of. If you're connecting to Mahuika, you probably want to just load a couple of modules. We don't need Boost here. Forge is nice to have. So I'm doing that here. Let me just move this a little bit out of the way. Okay, so I have a temporary directory, which is empty here. And the next thing that we're going to do is we're going to clone our little example code, which is called scatter. Copy paste, go to the web page, copy paste, or I can actually also put that in the chat. So we clone that. If you don't know Git, that's always a good thing to know. This is how we store, a lot of repository. Essentially, we're just pulling it from the website. So the next command we're going to type is scatter. cd scatter, and we have these different directories. Now the scatter code is just an example code. It doesn't really matter what the application is, but it's a wave propagation application. We have a wave coming from the left-hand side of that. We can see that on the picture. And then we have an object somewhere in the middle. The object, some sort of a potato shape object. And as the waves come from the left-hand side, they get bounced off and they reflect. And when they reflect, there's a bit of a scattering, hence the name scatter. So the other thing that you can see is that, as you move away, the waves are sort of nice little trains with a little bit of scattering left. But on the right-hand side of the object, what you can see is some sort of a shadow area. That's the area where, if you think of that object as being an island, then that's, you don't want to do any surfing on those beaches. You want to do them on the left-hand side. So the other important thing in this particular application is that and that's very common. Most applications have that feature. There are for loops, and in that particular application, there are basically 3 nested for loops. First, because we have a grid on that was used to solve the problem, and so we have a lot of x and y points. So there's an iteration over the x points, there's an iteration over the y points, and then for each of the points, essentially what we have to do to solve that particular problem. We have to add the contributions from the reflection from the object. And those contributions come from the fact that that object here is sort of discretized, it's broken into little segments, 128 by default. And so 128 segments will contribute to a wave, will have to be added. So three loops. The three loops tend to be are nested in that particular case. That's also important. When we talk in terms of complexity, we tend to say that it's an n-cube kind of complexity, meaning that if we increase the resolution by a factor 2 in every direction, x, y, and also in the representation of the object, then we end up with something that runs much slower, a factor 8 times slower every time that you multiply the resolution by a factor 2. So, I'm waiting, maybe giving people, a minute or two to catch up, and if you have some questions right now, I think that might be a good way. Should people ask the questions on the chat, or how do you want Megan to have people asking questions?
I think in that Google Doc is the best if you have something that comes up while Alex is presenting, and if there are heaps of questions, I can interrupt you or someone on that question doc, and we can pause and kind of rehash something. So just pop things in that Google Doc if you have questions.
Excellent. Okay, very good. So, I don't mind to be interrupted. Megan and others, if you see some questions coming up, then I'm happy to just pause and wait for a little bit and answer the questions. So we essentially have done the clone. We have the CD scatter at this point. There are two directories that are of interest here. I mean, there's a original. That's the original code that is not vectorized. We have to talk later about exactly what it means, vectorization, but it's just, so we can go there. So CD original, and we can either submit, a batch job as is done here. And so we have SQ -u $user. So that's pending right now. But if you're not running on NeSI, then you can also run the application just by typing scatter.py. And first, I mean, there are a certain number of default options that are good to know for that particular code. But they basically, you can change the resolution in X, the resolution in Y, and the number of contour elements. These are the nice little options to play with. And there's also a checksum option, something that gives you just a number if you, because we're going to modify the code. If this number changes, then we'd have broken the code. So just to check that we have something running. So normally, I have submitted a job to Slurm for the default problem size, but we can just very quickly just check that everything is working. So I'm going to use a very low resolution, maybe 10 values in X and 10 in Y, and NC maybe 10 as well. And then we want to print the checksum. So if that works for you, then essentially you're ready to go, and we're ready to talk about vectorization and how to get that code run faster. So let's go back to our queue to see where we're standing. We still PD here. It's still pending. It's going to get going afterwards. That's fine. We can just move to the other directory, the vectorization directory, and now start talking about vectorization. So let me just go back here. So as mentioned, I mean, this is part of a larger sort of a set of tutorials that were motivated by us helping users run better and faster on NeSI computers. So we're only going to touch one thing today, that's the vectorization, but you're welcome to look at the other approaches to improve the performance of the code. So, you know, Number, C++ extensions, multiprocessing, OpenMP, MPI parallelism, all these things are things that eventually can make a huge difference in the execution of your code. There's also a first set of modules about profiling, which we have delivered at various places in the past. So you can also use that. It's very, very important to do the profiling of your code in order to find out where the performance bottlenecks are. And so we jump right into vectorization or the module called vectorizing. And the objective here is first for you to understand what vectorization is. That's the first thing. The second thing is to recognize which parts of your code might actually benefit from vectorization. So you know, you want to be able to zoom in very quickly. And we're going to use two examples for that purpose. One where we apply a function to an array, to all the array elements. And then we're going to take a look at computing the total sum. Total sum is also quite relevant for statistics computation. We're going to touch a little bit about the differences between Python and R, and you know, I also want you as NeSI users or as a code developer to be also aware of the pros and the cons of vectorization, because sometimes they might actually be a little drawback. So vectorization is really, it's a programming style. So you can still, it's not something that allows you to do more. It's just a way of doing it differently. And the idea is that you can either have for loops, you know, where you execute the same kind of statement, but on a different set of data, or you can actually pack everything into arrays and just say, here it is, right? And so let's go back to our example of the jelly beans. We talked about the tweezers and we talked about the ladle, and so first the jelly, sort of the jelly beans, the container, the jar, you can think of it as an array, and inside that array you have 100 or more jelly beans, and then you want to apply some form of operation on that particular array. So in that particular case, well, you want to pick, you know, each jelly bean and you know, either eat them or just hand it over to your neighbor. Whatever that operation, that's a function inside the Python code. And so the for loop would be, okay, for each bean, pick and, you know, give to neighbor, for instance. That would be an operation, and that could be a for loop. But the thing is that for loops, you know, can be slow. They can be slow in a scripting language. And why is that so? Well, a scripting language has to do a lot of little things on top of a compiled language. A compiled language a scripting language has to sort of, you know, it sees an instruction and it says, oh, choose or select element of the array, and then it has to say, okay, what is it? Is it really an array or is it a string? Because the operation might be very different. Is it or is it another type of container? So there are a lot of little tests and a lot of little things that have to happen for a scripting language to be able to interpret essentially an instruction. And that slows things down because you're going to have perhaps 1 million iteration, and so you're going to do 1 million times those little checks. What am I doing? I'm picking up a jelly bean. What is, you know, in which array? Well, that's this array. Is it what kind of array is it? You know, how many elements does it have, so on and so forth. The compiled language like C and C++ and Fortran, they get rid of that because they recognize that pattern and they say, okay, we're going to just map that to something that is very, very efficient on the computer. So vectorization is something that can really improve the efficiency of your code. And when we say the efficiency, we're not talking about 5–10%. We're talking big. We're talking about a factor 5, 10, sometimes 20. So it's really something that is worthwhile looking at. Again, you know, if questions are coming up at this point, you know, I'm happy to be interrupted and answer some questions. I am a bit limited because I can't use my second screen because something was not working so great.
No questions yet, Alex, on the question doc. So
okay. So so we talked about for loops, but you know, you have other ways of iterating. And one of them is called the while loop. And the while loops are very similar to the for loop. It's just a little bit more flexible, but we don't often need that flexibility. And if you don't need it, stick to for loops. For loops, the difference between a for loop and a while loop is a for loop, you know ahead of time, you know how many iterations you have. You're going to have. That's equivalent to saying we know how many jelly beans there is in our jar. Sometimes you don't. So if you don't, then you're forced to do a while loop. A while loop would often be you know, the right construct if you were to read a text file or something and you just don't know how many words, you know, things are coming in constantly, and so you don't know ahead of time, or if you iterating in time and you know, you have to sort of split your time step and these kind of things until a certain condition is met. It's best not to have an if statement inside the loop, and that's true whether it's a compiled language or whether it's a scripting language. The if statements would be equivalent to saying, well, I don't want to, you know, I don't want to select every jelly bean. I just want the green ones. And by the way, they have to be of at least a certain size. You can do it to some extent, but that's going to slow you down. So if you don't need to do it, just don't do it. But sometimes it's something that is required. So the other thing that I should probably mention is that when we talked about the jelly bean jar and an array. And so in Python, you know, if you just install Python without any batteries loaded, as they say, then you're not going to have a real array container. I mean, there's something called array, but mostly what a lot of people are using is NumPy, numerical Python, in other words, and that's a module that you have to import. It doesn't come by default with Python, but it's used, you know, all the way across, you know, science, and almost everybody is using it because it's so much more performant than the built-in list container of Python. And not to say that there's anything wrong with the list container in Python, but it's just that the list container is, again, much more flexible. It allows you to combine, you know, integers with strings and dictionaries and sort of package them all inside a list. The NumPy doesn't want that. The NumPy array, it wants the same thing. And so you can't mix, you know, jelly beans with lollipops and all these other things. You know, it's got to be jelly beans. So I guess we we're going to go through an example. So the first example, we just talk it through, and the second example will run it and gives you a bit of an idea. But I encourage you to, at home or later to actually run that particular example. But it's a bit of a fake example, but essentially, we have we're creating an array of zeros. So first we import numpy, which is as we mentioned, and we notice that this array has how many 10 million elements. So it's a pretty large array of floats, 64-bit floats. And all what we're doing is that we're setting each element to the sign of the index. So we loop through all the indices 0 to 9,999,999, and we just set the that array element to that. So that's the unvectorized version of the code. The equivalent, and by equivalent means that it just returns exactly the same result, version of that same particular loop is there's no loop. The loop has disappeared. Poof. And so what's changed is that we created an array of integers, 0 to 9,999,000, and then we just apply the sign function to all those values, and it just does it, boom, not exactly in one go, but pretty much so. That's essentially going to call a C function, which of course runs much faster than a Python equivalent version. And if you play and you try this test at home, then you will find that it runs about 5 to 20 times faster. And now take a step back and you ask yourself, well, it's running faster and it's shorter, and it's just as clear. We got rid of the for loop here, and we're just using numpy. What happens is that numpy.sign is a function that actually can be applied either to single values or to an array. So we use that property. It's the same function, but it's going to do something different. And once it recognizes that ival is an array, then it can go really, really fast, be under the hood. It might be using vectorization, BLAS, and all kinds of things, might possibly be even running on GPUs if it's a slightly different version of the library. So all these things can happen. Computers love vectorization. They love to work with arrays. So that's, but they don't like to work with linked lists. That's very inefficient. And so I don't have actually an example with linked lists, but that would actually be even slower than the one that is listed here. So so far so good.
Let's see, I think there's a question coming up. Can you put vectorized loops inside an if loop? I don't know.
Oh, yeah, definitely. So if you have an if loop, then outside the vectorization, it's fine. Okay, so if you're above, but okay, if you have an if statement inside the loop, a little bit more work. Okay, so it's there are some vectorized functions in NumPy, such as any, all. We're going to actually see one. So it's a very good question. Thanks. I think just we have a little exercise at the end that actually will have essentially a bit of an if statement hidden inside the for loop, and we'll still be able to vectorize it.
Great. Thanks, Alex.
Okay, so I'm going to let's just do the simple the second example. So the second example, what it does, it's akin of a statistic averaging or sum. So it's called a reduction operation. So you have, again, maybe 100 million, I think 100 million elements in that particular case, and then we just want to add them all up. And so so that's a natural thing to do. We write a little for loop, and we start with our sum, initially 0, and we just add things up. So the vectorized version, okay, we have to import numpy now. And what we do is we create, essentially, instead of the I in the range, we basically create an array of, called a range, which has the same effect, but it's going to create that array for us from 0 to n-1, n being 100 million. And then we have another function. NumPy is great, right? It comes with all these functions. We just have to use them, and then we sum it, and we're done. And so these two versions really give you the same result. So let's play with that. So I'm going to just copy paste that version here. So first I have to do an Anaconda 3 module load, and I'm just going to just so we create, let's say, my sum, if I can write that, and it's a Python code. So we just introduce something here, and that's it. And I want to clean that up a little bit. Okay, that's good. And so I can time that function, Python my sum. So the time is a Linux command. So if you're on Windows, you might have to use your stopwatch. But we're just timing the execution here. And as this sort of runs on the left-hand side, we're going to talk about the vectorized implementation here, and so I can do it actually here. Oops, it's done here. So we just write down maybe 15 seconds. Right, it took about 15 seconds, and now let's do a vectorized version. My sum v. And so I'm just going to copy paste that piece of code here. And we do the same thing, but this time I'm calling v. And let's see what happens. And you can see that, it's 1.2 seconds. It was obviously, so it's a factor 12 faster. So that's how things work. Now maybe that's a question for the audience. Is it's always a trade-off. If I'm absolutely frank and honest, I mean, vectorization is not always recommended, but I'd say it's recommended in 90% of the I mean, it really brings a huge benefit in 90, 95, sometimes 99% of the cases. But to be absolutely honest, there's a little something that you had to pay for the vectorization, and I'm not sure if the audience noticed that, but I did create an array here. That array is going to take space in memory. It's going to require memory, and whereas this thing here doesn't actually require memory because it actually doesn't store all the values for I in the range. It just knows how to go from one value to the next, and so that version here will be somewhat more greedy in terms of memory. So you're going getting a factor 12 performance improvement. Everybody is very happy about that. Just keep in mind that if you really have a very big code that requires a lot of memory, then you might, and you're really at the boundary of how much you can use, then sometimes you might have to revert to this, but it's going to run very slowly. The thing is that it's not arising. It's not occurring very often because generally it's you know, if you really have a memory problem, then you may want to also think in terms of extending essentially the code with C, C++, for instance, or Fortran. All right, so we have now maybe the next 10 or 15 minutes. The idea is we're going to do a little exercise. So we have a partially vectorized version of the scatter code that we've seen before. So maybe we can actually take a look and see if what the queue said. Okay, so I think we were in Oric. So I ran that, and I know that my timings are in the are here. So it took about 1 minute, you know, close to 2 minutes, 1 minute and 53 seconds. So I just write that down. I can show you the script that we actually ran. That's also something that might be useful for people. But essentially, all we did was we've just put a time in front of our Python scatter, and we just used the default size for the execution, and then just put a checksum at the end, so that we can actually verify that nothing changes after we tackle that little exercise. All the rest is sort of boilerplate little things we all running in serial at this point. So I can go here. I can go into my vect directory. That's where we are here, vect directory, and we can try to solve, you know, that exercise. So what happens here is that we a lot has already been vectorized, but there is one function which is called isInsideContour. So I'll open that function here. That's in scatter.py. So that's a is inside. Okay, that's our function. Make it a little bigger here. Right. So you can see that that function, sometimes, you know, when we compute our wave, sometimes we have to figure out whether we are inside the object, because if you're inside the object, there's no wave whatsoever. You just, you know, in the middle of your island, and you can be sure that the wave is 0. So we have that particular function that has to be applied to every x and y point. And the way it works is that there is a for loop. Remember, we have to look for for loops. So here it is. That's the only for loop that we can see inside our function, and and it actually says vectorize the following lines. But essentially is we computing some expression. It's basically a cross product, which you know, is essentially an area with a sign, and we know that for every point, for every value of a, b, you know, for different index values I here, we should have that condition. And if that's not the case, then basically condition says that the area has to be positive for all the triangles that go from the point to the segment. And so you basically iterate over all these little segments, num-seg. You can see that here. Then it's only in that circumstance that you can say that the point is inside the object. So how are we going to do that? Well, we're going to remove the for loop, right? And we're going to have to sort of change that part of the code. That's what we have to do. So the thing is that you know, we have the index, that's our index here, and it appears here in that expression here as well, and so forth. But the Python supports array slicing, and so what we can do something like that. We can go back and just say, without perhaps fully understanding what the code is doing, we can say, well, you know, I can create an array, right? I can say something like that. I can just copy that expression here and make it work on the array directly. I don't have to actually loop through. So I'm going to comment that out, but still want to see it. Oops. So that's a quick way to comment a block of code. And so that's our expression, and we want to work on arrays directly. So essentially we have to change every index by the column little symbol, which means, you know, take all the values in one go. All right, it's going back to our jelly bean jar. It just means take the whole jar. It's not even taking the ladle. It's taking the whole jar. We don't even need the ladle. And the so we're doing that. That's fine. But the problem here is that inside is now an array, and we don't want inside to be an array. We just want inside to either give us 0 or 1, right? And so we have to add a little condition to that. And so what we're going to say is, if any of those array elements satisfy that condition, then no, all, I guess, all have to satisfy that condition, right? Because we start with true, and then we have, okay, yeah. So essentially it's going to be num_p all, right? All this condition has to be true for all the array elements. And so we're using the array notation. So at that point, you know, I just want to take a little step back and make sure that I've got everything right. It's easy to mess things up, but, you know, inside is true. Then we have, for each loop, we want everything has to be true, and then we return true. So I think that should work, but we don't know until we try it, right? So I go back to my previous little window here, and I'm just going to copy that little command, Python. So I'm going to type the same command, and maybe, and, you know, remember that number, that's the checksum, 95.93, and then 484 at the end. So so with a little bit of luck, yoo-hoo, yeah. Okay, so so that basically that proves that we haven't actually introduced a bug, and now we able to just submit another job, and it's called scatter.sl. It's the same script as before. I can just take a look at it. So, you know, we have srun time blah blah. So we can just do sbatch. Just type. I mean, if you're just running on the laptop, you just type this value here with the time command in front, and you should be ready to go. So we have our job. I'm doing an SQ. It's pending, and it's going to work its way through the queue. Now, any questions so far?
There don't seem to be any new ones on the question document, but if anyone has something in mind, you can unmute yourself now while we have a moment. Any questions or comments so far?
So if not, then I just continue and just feel free to ask any questions about any part of that particular tutorial. I'm happy to answer that. So the okay, so it's done already. Oops, no, sorry, was it running? Oh no, it's still pending. Okay, so we ran that particular case. Just we should get the same timings, but here we just cut the chase short. So this is the speed up. So the higher the better. And so the original code that was not vectorized for the standard size problem, we just say that the speed up is 1. And in this particular case, you can see that there's more than 6x speed up. So it's something that is quite significant. It's really the difference between you're going on a walk, or you're driving your motorcycle almost, or you're going on a jog, and you're driving at a leisurely on speed on the road. So it's something very significant. We love to hear from you. If that's something that works for you, you can always come back and ask more questions. Again, this is not the only strategy that you have at hand. There are other strategies as well. And if you go through these examples and where you can learn about using number, that's again Python only stuff, or calling the C++ extensions, again, specifically for Python, or doing multiprocessing, OpenMP, MPI parallelism, and so forth, then you should get something that looks like this kind of speed up. So it's maybe a little difficult to read, so I'll make it a little bigger here. But so we have, this is a speed up on the left-hand side, so the higher the better. We had the original code 1, so we can hardly see it, but we can see that vectorization brought us this. Number is something similar, but it would actually translate the code automatically for you. You don't need to know any C++ into C++. You have C extension. That's when we actually write an extension in C. We just decide to write the loop in C. So we get an additional little factor. It's a little better than number. And there are 2 versions, actually. They're always different ways of doing the same thing. And so you sometimes want to experiment a little bit. You get about a factor 20 plus. And all these strategies up to here, they don't require any additional resources. So you're just running on 1 processor, 1 core, you're just running 20 times faster. If you go further, but of course there's more work involved in that. The vectorization, you only need Python. Here you need Python, but you need to install that number package, not a big deal. And here it requires a little bit more work. So nothing is for free, not even jelly beans. So now the light, so cyan-colored bar graphs are the ones that are obtained by using more resources. So once you reach the point where you have achieved the maximum performance per processor, then I think that's a good step for you to start thinking in terms of parallelism. And you have multiple ways of going forward with that. These are just a few of them. Multiproc, that is a multiprocessing. That's a Python module that comes with Python out of the box. We have MPI. This is an MPI version in Python. So in that particular case, depending on load balancing and different details, it brings some benefits. But actually, you can see that C extensions actually work even faster. And for this particular problem, your mileage may vary. We found that more than 100 speed up with respect to the original problem if you use OpenMP, which is multi-threading. So in this particular case, 8 threads. And the second version of the C extension seemed to work really much better in terms of parallelism. So you can really see that big differences between slightly different implementation of the same problem. So that's not the end of the road. You might be able to come up with an even better implementation. If that's the case, please let us know, and always happy to talk to you or talk about your software. We have many people may not know, but we have a consultancy program at NeSI, which specifically helps users achieve the best performance. And so you can always file a little ticket to support@nesi.org.nz, asking for a consultancy support, and we'll take a look and we'll discuss and see if that's something that we can do.
Thanks, Alex. Are there any questions or comments, things that you've learned in this webinar that you feel compelled to share before we do a little bit of a wrap up? I'll just pop some slides up again, Alex. So if you could stop sharing your screen. Cool. Oops. Sorry, my Zoom went away. Can you guys hear me? Can I get a verbal? Because I've lost my Zoom screen. I can't find it on all of my my pages. I'll find it. Just a second.
Oh, thanks, Megan. I thought I was the only one actually to have some Zoom problems.
No, it was just there, and now just for after. Let me resume. Oh man. Anyway, I'll just say it out loud. And if you have questions, feel free to chime in. But just some takeaways from today. You can vectorize your Python scripts with NumPy to get a free speed up. And other libraries exist for other languages. If you have more questions, definitely email us at support@nesi.org.nz. And vectorizations is most effective for loops where most time is being spent. So if you want to check out our material on profiling, which Alex referred to earlier, we have a recording of a workshop we did on profiling. And profiling is just referring to finding those bottlenecks in your code so that you know which parts of your code you want to be vectorizing in the first place. And it's always a good idea to start small when you're vectorizing your code. Make sure you have some unit tests to ensure the end result of your code is not affected. And of course, if you want more help, please do contact us at support@nesi.org.nz. We would really love to hear from you. That's all the takeaways. Any last minute thoughts or questions from the crowd?
I guess one question was whether, how do we know whether it's worthwhile to do the vectorization, right? Because I talked about that increased memory footprint. And I mean, usually, I guess if you're not close to the memory limit on the node or on the per core, then it's usually which is I think about 3 gigabytes or something per core, if I recall that correctly. Somebody should probably vote me if that's not the case. Whatever it is, it's in the gigabytes, and if you're just using a much smaller amount, sometimes you can, on the back of the envelope, you can estimate the amount of memory that you need. For instance, we had 100 million elements in our array, and they were in integers, so that means 32-bit, or that means 4 bytes. So you just take 100 million times 4 bytes, and that should give you 400 megabytes. 400 megabytes is not a lot these days. So in that particular case, it was a clear win. I guess to me, I mean I'm not going to probably spend a lot of time doing some vectorization if I feel like I'm going to rewrite the code in C++ anyway. And then it's a little easier to translate the code into C++ if you have the for loops, because of course the C++ or the Fortran code doesn't know anything about NumPy and these functions. So when you translate the code, then it's a little bit more work. I guess to me that's really probably the biggest drawback. I've never encountered a case really where the memory was a limiting factor. Usually there are other things that show up before. Maybe other people, maybe Wolfgang or Chris or other team members or Albert or have other may want to add to this.
Let's see. I think since we are at time now, maybe we'll just go ahead and wrap it up. But like we have said, if you have any other questions, do get in touch with us. So thanks again, Alex, for your presentation. And that's it from us for today. The webinar is now over. Thank you guys so much for coming, and have a great afternoon.